First of all, I think I was hoping to get to see The Martian last night, but we actually had a really cool social media event on this workshop, and there was a lot of interest in what we're doing. So unfortunately, I couldn't get to the movie, but I heard it was a lot of fun. So hopefully, it was for all who went. We are getting a lot of interest on the publicity side, which is sort of indicative of, I think everyone, I don't know how you feel, but I kind of feel like we're on to something here, but it's be murky, but that's okay in the beginning. A couple of admin things, and first of all, I want to also welcome our Ustream audience. We've had a really great participation, and we're actually counting on you for ideas too. The sort of administrative things, one, can you share the email address, please? That's up to, so just for the people that are on Ustream, we do have this email address. We are going to keep putting this up here. We are getting feedback, which is wonderful, and so please keep it coming. And then a reminder about the coffee, much better yesterday, so many thanks to everybody, but donations are really key to making sure we all can think, and we're going to do it anyway because we need everyone fully primed as we go along. We are going to send out the pictures that are actually available on the internet already for the group picture, and we're going to send out a link to that. It'll probably be this morning as soon as we can get it out to you, but they actually look pretty cool, so we'll get them to you. A reminder, Lindsay, where are you? The scorecards for these sessions, we really would like for you to fill them out. You know, most important is listening to the presentation, but we really would like to get that feedback. We're trying to approach this feedback from two angles, really, and I'll explain that more tomorrow morning. But your ideas are key there, and that's a mechanism that we've come up with for this session to try to do that. And we're going to ask your feedback on them, too. And then a reminder about tomorrow. Tomorrow was really kind of a wrap-up thing. We're really hoping everyone can say we need your ideas, and there's going to be two formats. But we'll talk more about this idea of prototyping and what that means. But we really want the people who were here in the sessions, pros and easies, to be here if at all possible. So that's kind of a key piece. The other piece is a lessons learned, future steps. A document that we showed you the questions, so you got them in advance. Take a look at them, and we'll actually, when we send out the picture, can we send out the link to that document too again, just so everyone's got it right in your inbox. And we need your ideas on that thing. You're a part of creating this future, as murky as it is, and we need you to, hey Jim, to really be thinking about what we learned that worked well here or did not work well. Both are important. And then what are the other things we need, to start really flushing out the solution space, some of which may actually drive a potential orbiter in the future and that kind of thing. So we really need your ideas. So look at those questions, and you'll notice at the bottom of that list is a question that says, we don't know. Tell us what the questions we missed, because we really meant that. So please help us with that. Okay, and that's all I had on my little list. And next is Steve Hoffman is going to help me with this session. And then we'll get it going. One of the presenters, we do not have his presentation. We're not even sure where he is, frankly. But that's okay. It buys us a little margin. We've been running over on these things, so that'll all work fine. We'll hopefully get his pitch out to everybody so you can look at it too. Steve, you want to take it? Thank you. Yes. Gianni. I know, but we were trying to find...
So let's bring up that newsletter for a moment. Rick, can I have the remote mic, please? As Rick mentioned, there's some questions that are out there. Everyone that is attending here should have received an email that looked like this with some information in it. So if you can scroll down, please. Near the bottom of that, there's a link. Right there, he's pointing to it. It takes you to a file that looks like this. So it sounds like we may send that out separately, but if not, you can see it in your, you can get to that through the hot link in your email. This is a list of the objectives and the objective we have for this document that Rick was referring to, and the uses that we anticipate right now. It may not be an exhaustive list, but it's fairly comprehensive. The rest of the document, just go down to the next page, and that should be sufficient. The rest of the rest of this file is roughly a rough outline for the document itself. So the major bullets you can think of as section headings. And if you would look through this, please, there's a list of questions or statements for each one of these sections in this document that we'd like you to think about, and that's what we're going to be talking about tomorrow. And we will have some time past tomorrow for you to provide some inputs too. So if you think of something next week that you didn't remember while you were here or just occurred to you on the plane back, you can send those to us and we will incorporate those. We're going to give ourselves about 2 weeks to come up with a first draft of this thing, and then we'll see what changes we want to make, what additions we have to meet. But we're looking for your feedback to be included in this. So please look at these to give you some idea of the kind of feedback we're looking for.
Let me add one thing too. Sorry, I didn't mean to interrupt that flow, but I also want to mention that the rovers from JSC will be coming over here today. So if you see something looking very strange in the parking lot, that's what they are. But anyway, our intent is to actually have people take a look at them real closely this evening, but they will be coming in today, just so you're aware of that.
Okay, so any quick questions about this? Otherwise, we'll get right into the sessions here. So we got a little bit of time. All right, then we have, we had 5, now 4 papers for this morning. They're all typically centered, or at least named after major crater features on the surface. And the first one is by Mikowski et al. And Joe, I'll turn this over to you. We're starting off in the northern hemisphere. I know we jump around between or north and south of the equator. So please point out where your site is.
Okay, it is here, next to North Vallis. Okay, so actually I want to indulge a little bit in some big picture thought. I hope that's okay, first thing in the morning. I think it's maybe the appropriate time. And I will get into the rubrics and all that later on, but I feel like it's important to mention that in this whole process, we actually have a couple of decades to raise a generation of literate scientists that are going to hopefully be on board with us, and that will actually help with our sustainability and seeing this through. So I want to keep that in mind, because what's really important to me is communication among us, communication with them, and being clear between engineers and scientists and among scientists what matters most. Because oftentimes we have different levels of expertise and different types of expertise in this room. We don't value the same sorts of results. But for example, Earth scientists maybe sometimes see themselves in competition with what we're trying to do, but we can get them on board by explaining why Mars is so important. I'm going to speak a little bit about that. And when it comes to priorities among us, what drives this sort of endeavor? Let's say for argument's sake that it is science. Well, maybe it's life detection, but for me, maybe it's more important to think about prebiotic chemistry and what was the solar system like at that time, so that we're not married to the binary outcome of detecting life or not. So to me, I'm hugely interested to understand what was going on Mars or on the Earth at that time when life arrived on Earth. So the most ancient rocks on Earth are rare, and they're very hard to interpret. They've been smashed up, mangled, and mashed by temperature and pressure. So the analogy I like to use to people is that it's a bit like looking at a graffitied wall, which has been painted a number of times, trying to imagine what that first generation of graffiti is like. And no matter what you do, you can't strip all the paint away, and you're inevitably going to be stuck with using your imagination a little bit to link that bit here and that bit there and that bit there. Becomes a bit of a Rorschach in some ways, but it's just difficult. In fact, I would go so far as to say that we'll never understand truly the origin of life on Earth by staying on Earth. So that speaks to point number 2, that if we communicate with Earth scientists, if we try to understand each other, that this issue, going back in time, we get to a point where after about 3.7, 3.8, there's just no crust. The oldest rocks we find seem to maybe have prokaryotic life already. How did it get there? We may never, ever figure that out, actually, because these rocks are so messed up and because there's nothing before it. Maybe we need to go somewhere that would contain unmetamorphosed stuff of similar age that we can study. Okay, so Mars. We have the good stuff here. We have crust that is that old. We have crust that's well preserved. We have igneous, sedimentary, hydrothermal deposits. We think that life on Earth was potentially hydrothermal, chemoautotrophic stuff at that time. We don't really know what was going on. Frankly, it's very important and very healthy that we understand that we don't know what we're talking about with a lot of this stuff. We think we know a little bit, but we're really in our adolescence of understanding origin of life stuff. But we do, it's clear that very, very cool stuff was going on Mars at this time, and if we go there, we're going to learn things about organic chemistry. Life may or may not have formed, but whatever led to the formation of life on Earth probably was going on in Mars as well, and is preserved. So, I'm a fan of, well, here's how I think about Mars, and I really hope that during the Q&A, somebody who thinks about this kind of concept all the time will ask a question. I don't understand why a lot of the interest on Mars surrounds surface environments, because I think about Mars, I think, well, it's further away from the sun, so straight away, you have less solar energy available. You also have this faint young sun idea. Could be right, could be wrong, but that's something to think about. And the surface was a real drag most of the time. Lots of UV, hyper-arid, not really where you want to be if you're a bug. So why do a lot of the assumptions about surface environments really are ultimately rooted in the idea of photosynthesis. So whether or not that's important for Mars, I don't know. I like the idea of, this is so kilometers of crust in this diagram, the idea that you have fluids down there interacting with rocks, producing potentially free chemical energy for organisms in the subsurface. That's kind of more interesting to me, whether you sample those rocks themselves or places where those fluids emerge at the surface and carry with them some signature of subsurface stuff. So, yeah, that's something I'd like to talk about. Now, and on Earth, by the way, we think photosynthesis didn't come around until about 3 billion years ago, so you're end of the Hesperian. That's the way I think about it. Maybe wrong, and I would like to be educated, or would like to have that discussion, actually. So, here's the thing. McLaughlin Crater is here. This is the site I'm proposing. It's near North Vallis on the dichotomy boundary. It's a very deep crater, and the reason I think it's interesting is because it probably contained a lake, almost certainly. It doesn't have any big channels flowing into that lake, so you have to wonder where the water came from. There are some tiny channels in there, but they're just in the wall of the crater. So it was probably fed by groundwater, potentially a hydrothermal lake. It's very ancient, about 3.8, 3.9 billion years old, and it also has chunks of crust that have failed in the wall of the crater and flowed into the center of the crater that contain probably hydrothermal deposits from the subsurface around here. The idea being, okay, McLaughlin Crater, it's about 100 kilometers diameter, probably had a lake about 500 meters deep. There are a number of reasons for that. I can't go through all of them right now, but basically you have some channels that terminate along the wall. You have some very, very poorly developed delta-like features. That's a little bit liberal use of the term delta, but in fact you do have cross-bedding and things in here with alteration minerals and that sort of stuff in downstream from channels in this platform deposit. So where all the channels terminate roughly. So that could be the indication of a delta. You have layered, most importantly, you have layered stuff down here that has all kinds of carbonates and clays. So from CRISM, we see very strong features, vibrational features related to water and carbon-oxygen vibrations. And these are among the strongest that you'll see on Mars. They're in a handful of detections that really stand out. So it's not an ambiguous detection in any sort of way. Probably magnesite, hydrated magnesium carbonates, and also iron-rich clays and smectitic, maybe mixed-layered stuff. Here's what that crater looks like looking toward the east. So you have this crater Kirin on the southern wall, which is put ejecta down in the crater. You have some weird flow-like things, which are probably related to ejecta, but also debris flows, layered deposits, which will be science targets, and also resource targets on the floor. And I won't speak about it too much. I did in the abstract, but looking at in this meeting, I feel like we have so much to digest. I'm not going to talk about all the ROIs that are outside here. Let's focus on what's interesting in here, because we don't need to talk about that. The idea is maybe you can actually drive out of here someday and have a super long presence. But we can speak about it in the Q&A if you want. Pretty much here's the exploration zone. So centered in the crater, you have all kinds of good stuff to do in here. And then we were just looking from here toward the east, and the question is whether you could drive out and go check out the northern plains, North Vallis, Noachian terrain. So one of the advantages is that you are at the triple junction of 3 different kinds of terrain, where if you want to have a long-term presence, I think that kind of diversity is important. But inside, you also have just super cool geology inside. Here's a summary of what the ROIs say. In terms of resources, this isn't a place you're going to go if you're looking for ice. If you need sulfates, really hydrated sulfates, this is not for you. We would have to get our water from clays, different kinds of clays, and maybe hydrated carbonates. I frankly know nothing about getting good stuff out of carbonates, so that's a discussion to be had. But there are, the carbonates seem to be hydrated based on CRISM. The good news is they're within ejecta and debris flow stuff that would require probably a wagon and a shovel to excavate. So that's good news. And in terms of science, layered, ancient, hydrothermally fed, or groundwater fed, I should say, lacustrine deposits, iron-rich clays, lots of carbonates, and then if you get out, you have this kind of good stuff, the Marth-type clays. But even just in the crater, if I was interested in exobiology, and I am, I would probably just dig into these thick, tens of meters at least, thick stack of hundreds of layers of carbonate and clay-rich materials. Whatever's in there, be it life or other stuff, it's going to teach us about what was going on chemically early on in the solar system. I actually had loads of ROIs in the abstract, and so I just didn't think it was a good use of time to go through every single one of these in the talk. It's more fun to sort of think at the summary level and some specifics. So this is the landing zone, which is in the center of the crater right here. All right, here's the crater, landing zone there. The things I'm going to speak about are, in the immediate vicinity. Okay. Landing zone, there. First thing we do, science, ROI number 1, datable surface. This is a big issue. We're going to, because I think people have very strong feelings about that, and I don't know very much about it. So let's chat about that. The other thing is this Monument Valley sort of area here, where you have lots of layered carbonates and clays, and then you have a debris flow or an ejecta material there that flows into the basin floor. So these are datable surface, clays and carbonates, clays and carbonates, clays and carbonates, but less strong. You have all that kind of stuff. Now, what do we mean when we say datable surface? To me, this is perfectly cool. This is probably an ash fall deposit. It's dark. It's datable in terms of crater counts. One has to be mindful of draping because it's thin enough that it could drape some craters, and your crater counts can deceive you. But assuming that we have the best crater counting minds dealing with this, we have dated similar surfaces in Marth to about 3738. This is the kind of stuff that you could, it's probably got materials that can be dated. Okay, 5. I'd like to have a discussion later about whether this satisfies people's desire to I understand perfectly well. Dating something is hugely important, and unambiguously, we get one shot, we need to do that right. Does this qualify? I think it does. In fact, I would say going to a lava and a suite of lava flows, dating any single one of those, has its own set of ambiguity. So it's not just clear cut that you know what you're getting because you go into a flow field. This has its own set, but I think it would do the job. And it's a marker bed present throughout the region. Now, in terms of primary science, ROI 2, you have layers like this, loads of clays and carbonates. Very interesting in my opinion. You have active erosion backwards. One of the things we talked about in Gale Crater was exposing layers that haven't been getting whacked by cosmic rays and things for a super long time. I think you have the opportunity for that. Can't say it's for sure going on active erosion today, but you probably have fairly youthful surfaces. We know that because you see, this is also in that same ROI, you have flat areas where you can scoot around pretty quickly, but you have some buttes that are eroding back. And if you look at this in color, you see different levels of what appears to be oxidation state. So that would indicate probably more and less youthful surfaces potentially. I love this image. I don't know if you can see how well it comes out, but this is, again, clays and carbonates in the floor of that crater. You see unconformities buried within here. Cool stuff. All right, the debris flow / ejecta, I actually think it's both. If you look at it in really high resolution, like HRC, DTM data, you can see areas where there's definitely ejecta, but then the wall has failed as well. So you have secondary debris flows temporarily disconnected from the primary impact event. These things have huge blocks of carbonate, have a lot of clay. It's very cool stuff. Accessible. So scientifically, that tells you about material that was in the wall of McLaughlin Crater, so in the subsurface. You can study subsurface processes by studying that stuff. And then you can potentially understand if things could have been ejected into a wet environment. Could be. Don't know. But there's basically no primary mineralogy left in there. Very strong features. If you're used to looking at CRISM data, wow. Rubrics. I just made it all green. No, I'm joking. I think it's more important what it's not, right? So what is it not? Amazonium, I don't think it's important. I wouldn't go there anyway, but it doesn't have that. Near surface, well, it's my opinion, I don't know. Near surface ice, don't have that probably. Remnant magnetization, good luck with that. And then as far as ROIs go, again, probably not much ice. Don't have that. This stuff, I don't even know what this means, actually. It's a silicate planet, so you have that. Not to make fun, but no, really, this is an area where I don't fully understand what's going on, so I didn't fill it in. But that's kind of, it's what we don't have. We don't have a lot of ice. So if that becomes important, this isn't the site for us. So I'll leave it. Oh, there's a paper. The problem with McLaughlin is there are not loads of papers on the subject. It's something we've run into in March in the 2020 discussion. So this one is available. This one's open access, which is not really about McLaughlin, but it's about detailed clay chemistry. So that's something to have a look at if you wish. So I have a spare minute, but I'm going to leave it at that. Yeah, that's it.
Our next paper is by Gian Ori, but I don't believe he is here, right? Okay, so we'll move on to the next one by Lynch and Ray. I saw Ms. Lynch here a moment ago. We're going to jump to the southern hemisphere now, and I'll turn it over to you.
Okay. Just kind of like, this might not go through my hair. The joy of, yeah, that's not going to go over my hair. Let's see. Okay. Hello. It's right there. It's my best in Vanna White. Good morning, everybody. Wow. Thought I'd have 15 more minutes to kind of practice, but I'm ready to rock now. Okay, so this morning I'm going to talk to you a little bit about a site that I've been kind of studying from an astrobiologist point of view. And just to let you know, I am an astrobiologist. I'm a geomicrobiologist. I'm not a planetary science, so I apologize now for the mistakes that I'll probably make on some of the geology. So we're going to talk a little bit today about Columbus Crater, which is in the Terra Serenium. Yeah, I already did, but I'll do my Vanna White again. It's over here. In the Terra Serenium region of the Southern Highlands. Let's see. Sorry, make sure I do this. Right. So Columbus Crater is about 110 kilometer diameter crater, so it's pretty much the entire exploration zone, and we'll get to that in the map in a minute. It is the prevailing hypothesis that we're going to just kind of stick with today. I'm sure there's others, but we're going to stick with the prevailing one, is that it is a groundwater-filled Paleolake basin. It's a closed basin that was filled up to about roughly 1,000-foot depth from groundwater upwelling. And it's estimated that there's approximately a 1.5 kilometer depth of sedimentary and or volcanic infill within the basin. You can't quite see it here in this image, but there's excellent crater retention. There's a lot of nice small craters in here. As you zoom in and get more resolution, that would be great for age dating. And there's a diversity of Noachian and Hesperian age deposits. Mainly, the crater rim is dated in about the mid-Noachian. And then the aqueous deposits are the late Noachian to early Hesperian. And then we have these interpreted lava flows over here that are probably more late Hesperian in age. And most importantly, at least from my perspective, from astrobiology and scientific view, we have a diversity and a whole bunch of aqueous mineral deposits throughout this basin and throughout almost every ROI that I'm going to talk about today. So why am I, as an astrobiologist, interested in this? I study extreme environments here on Earth. I am really interested in understanding how life works in extreme environments that are similar to Mars, and how we can kind of understand what kind of life would have existed, specifically in that transition period when Mars was kind of transitioning from that surface water period to maybe that more groundwater dominant period, and that late Noachian to early Hesperian transition. When basically the planet's starting to dry out. I'm interested in habitable zones that would have been happening in that transition period, and so I study analog environments such as the Great Salt Lake, the Pilot Valley Basin of the Great Salt Lake Desert, out in northwestern Utah. The reason that this is a very interesting basin is this has an active groundwater system, and it's a brine water ground system that fluctuates through the upper about 8 meters of the sediment here in this basin here. And not only do we have a lot of interesting similar mineralogical diversity in this basin here on Earth that we have in a basin like Columbus Crater. We have a lot of phyllosilicates, we have a lot of carbonates, we have a lot of polyhydrated sulfates, and of course we have chlorides, which we can't necessarily see in Columbus Crater, but they're here. And I'll shamelessly plug my paper where we did some analog studies, Lynch et al., and JGR Planets 2015. But I'm also interested not just in the analog materials, I'm interested in the life that exists in this basin, and we actually have a lot of diversity in the near subsurface of this basin. And this is what we would probably be able to start looking for, is the kind of life that lives in this near subsurface, supported by the groundwater flow going through this basin, and then eventually being preserved in these subsurface sediments. And so this is a wonderful environment. I think that's an analog to the kind of features that we're going to discuss in Columbus Crater. And personally, I think it's a great habitable zone to look for biosignatures and biomarkers for life. So moving on, we've got, this is my beautiful landing zone here. We've got 5 nice little ROIs we're going to talk about, and I know you see a really big ROI about the crater rim. We'll get into that in just a minute. And then we've got 1 resource ROI. For the landing and habitable zone, I basically just kind of put a 5x5 square kind of in a nice flat region in the northeastern corner where we're pretty sure it's pretty smooth. It's pretty smooth and pretty flat. This whole basin is really is pretty flat, mostly high thermal inertia, so a nice, strong, good surface for landing. And of course, the altitude is a little higher than most other basins that we've talked about today, but still kind of qualifies. So science ROIs, we filled in ours, made our best guesses. You guys can take a look at that. Resource ROIs, we not quite sure, so we could really use some help from some other experts to kind of help us maybe think through the resources that would be needed to kind of fulfill some of these requirements. So again, like I said, I just put a kind of a 5x5 square. So this is kind of the landing zone and field station region, nice and flat. We need probably some more coverage to make sure that this is a good region for landing and for a field station. But this is probably one of the flattest regions and least varying regions in the crater basin. So our first science ROI is the northeastern corner of the crater, where we have the largest, most exposed light tone deposits and the highest diversity of aqueous mineral deposits kind of exposed in this whole region right here. And there's a whole diversity of different geological forms that we see here that are kind of that correlate with these aqueous mineral detections. So one of the first, and these are just a couple of examples. So the first example is just this nice mesa here with these moats that are interpreted as lava flows kind of around the mesa, these mesas with these light tone deposits. The second would just be kind of these really nice outcrops where you can see the light tone deposits, which are most likely the aqueous mineral deposits. And we have basically what we have all along the rim of the crater and the crater floor and going up the rim, we have these nice stratigraphic sequences of these aqueous deposits. So we have the polyhydrated sulfates overlaying like the jarosite as an example. So science ROI number 2 is this crater I call the D11 crater, basically because the diameter is 11 kilometers, so it's the D11 crater. And this is kind of located centrally in the basin, kind of more in the southern portion of the basin. So it's got it's a really nice crater. We do have a possibility because of the slopes here. There may be some possible RSL. We have not investigated that, but it'd be really good to get some time coverage here to see if there actually are RSL existing here, especially since this is a James Ray site and they're the RSL team now. The nice thing about this crater is that we have this beautiful stratigraphic context within the crater as well that gives us an idea of the actual sedimentary sequence. So we have these light tone deposits here that are overlaid by these dark tone deposits that are most likely lava flows. So these are probably our aqueous deposits here, overlaid by these dark lavas. And most of our aqueous deposits in this crater here are an unknown hydrated phase, but we definitely know we have some kind of hydrated phase in this region. The big and most interesting ROI is the rim of the crater itself. So this is Science ROI 3. And it's basically because we have this characteristic polyhydrated sulfate ring that literally circumvents the entire crater. It goes all the way around the crater. And we have these beautiful, nice layered sequences that we can see all along the crater wall. In some places it gets disjointed or whatnot, but it basically does move all around the crater wall. So basically, you drive in any direction, you get to the crater rim, you're going to encounter this. So anywhere, even if we have to change the landing site within Columbus crater, we can still access this somehow because it's everywhere along the crater wall. And as you can see, when you kind of zoom in, you see the beautiful layering of the different polyhydrated sulfates with the gypsums layering with the magnesium iron sulfates here in the rim. Science ROI 4 is kind of centralized. It's this pedestal crater that's overlaying this beautiful graben here. Again, another example of kind of these light tone deposits from this pedestal crater. And more importantly, we have this beautiful graben that moves through the center of the crater and could be related to regional processes. And more than that, might even be actually where the water could have upwelled from. That's one of the prevailing hypotheses. And we can go here, study regional processes, and study whether or not this is where the water came from. We also, kind of in the southwestern region, have another a nice set of large dual impact craters that would allow for us to study cratering processes. Also would allow us to study some more deposits that are within the basin. And if you look down here, you can also see we have these interesting flows here, and they're mostly made up of iron magnesium phyllosilicates, whereas most of the basin is aluminum phyllosilicates. So it's kind of interesting that we have kind of more of a concentration of the iron magnesium phyllosilicates here. So finally, our resource ROI is the central peak, which kind of is almost literally the central of the basin. The central peak is mostly made up of, at least at the base, made up mostly of aluminum phyllosilicates, which is the green, polyhydrated sulfates, which is the blue, and some monohydrated sulfates, which is kind of the red. And what's interesting here is that even though most of the basin floor has got a high thermal inertia, here at the central peak it's more of a low thermal inertia, so there's a lot of loose fines here. So that's why I chose it as a resource ROI. And if you look, you can see you have these beautiful aeolian bed forms that basically are just kind of in and around the entire central peak here. So this might be a great place to go and pick up your material for some aluminum phyllosilicates for your building materials, or your polyhydrated sulfates for your ISRU for water, after you make sure there's no biomarkers in them, of course. So data coverage, we're really good on CRISM data coverage. It looks pretty good on just general data coverage. There is kind of a little spot here in the wall that we would like to get some more coverage on for just general CRISM. And high-res coverage, we clearly need a little bit more. It's not as good as we like. We have good coverage on our ROIs, but there's a lot, on most of our ROIs, but there's a lot more that we'd like to get. So our highest priority coverage would be, and I'm sorry, this should be high-rise stereo. That's my bad as not as knowledgeable of the planetary tools. Should be high-rise stereo coverage of the crater rim and basin floor, and that's so that we can get an idea of whether or not the astronauts can actually traverse up to the crater rim. Can they actually traverse up the crater rim and be able to explore the crater rim? CRISM coverage of the North crater rim to kind of close in that open area. General high-rise coverage of the crater rim and the basin floor to get some more detailed imagery, and that would also help us with traversability as well for science. And then for resource coverage, again, more general high-rise coverage of the basin floor to be able to kind of understand and look at more of the materials that are there to get a better understanding of what our materials are going to be easy for ISRU and other resource use. And I think that's everything. Yep.
Thank you. The next presentation is going to be on sites in and around Huygens crater, and Paul is not the primary author, but he's the speaker today. You want to point to your location, please?
right. So Huygens Crater's right here in the Southern Highlands. So what's different about this place? You guys keep hearing all these places. This is in the Southern Highlands. If you look at it, it's sort of it's not surrounded by much of anything else. Not many people proposing craters in here. This is an interesting spot for a number of reasons, and I hope it's also one of the highest elevation sites being proposed. So I hope this helps sort of allay the concerns that everything interesting is below in the low elevations, because I think there's certainly lots of interesting stuff in the high elevations. Anyway, so I'm not the first author. Sheridan Akis, James Ray, Kim Selos are the main science authors here, and I'm really happy to be here and help sort of carry on their message a little bit. James was able to make it today, but the other two weren't able to make it. So I'm interested in this site because of the carbonate story. So Joe Michalski and I wrote a paper about carbonate in right around in this central peak of a crater right here, and we've heard about carbonate in Nili Fossae, and so these are some of the other detections that James and his students and Bethany, I think, Elman, have made, and it's really interesting because most of these down here are all carbonates in central peaks, and they look like they represent subsurface layers that have been brought to the surface. And it's very interesting that this is really the main place on Mars where you find carbonate. There's a little bit of carbonate in other places, Gusev Crater mainly, and we just heard about McLaughlin. But this is one of the main concentrations of carbonate on the planet. And it's got me sort of interested that why we keep finding it all in the same spot. Now, there's a pretty good exposure, so that could be a reason. But there's also, I'm also considering the idea that this area was an ancient carbonate deposit that has been either buried or it formed underneath the surface. So conditions in the Noachian were able to form carbonate in this area, and a carbonate region is a really interesting region for a lot of different reasons. Obviously, in order to form carbonate, you have to have carbon. So as the carbon source, it's an interesting spot. Carbonates indicate alkaline conditions. That's also very interesting. So astrobiologically, the fact that this is underneath the surface, it represents liquid water, and it has the potential to sort of when there's carbon sources present, it gives us a lot of reasons to think that this might be a really nice habitable environment, or was a habitable environment. So the idea here is that you have this deeper alteration that either happened in the subsurface or happened at the surface and was later buried by a basaltic crust, or maybe impact from Hellas that covered it up. Also, we have the Syrtis Major lavas that covered things up as well. So you have a couple of different ways that you could have covered it up. It could have been at the surface. These central peaks, these craters are bringing up, the big enough craters are bringing up this deeper alteration to the surface. So Huygens Crater is sitting right here, and several of the detections are around the rim of Huygens. And you can see so this is Sheridan's map of the crater itself. And we're focused right here where this crater here is in this yellow spot. So these are aqueously altered material. The crater itself is filled with high calcium pyroxene or an olivine. So it is lava flows probably from the Noachian and early Hesperian lava flows that filled in the crater. The science ROIs here are, so sort of back and forth here. You can see topographically, you can see these, that this area is really also very interesting with regards to valley networks. You have a lot of channel formation on the crater and around the crater. And so the science ROI is going to come back. Okay. So we're focused on this crater right here. It's an unnamed crater, and where it's punched through some of these lava flows and revealed this aqueously altered material. This aqueously altered material includes phyllosilicates and carbonates. So our landing zone is right here on the edge of this crater, and we have science regions of interest all around, exploring the crater rim, exploring the valley networks, and as well as these lava flows, which provide interest for volcanology, interior science, as well as chronological dating. So, so this is this unnamed crater we were looking at, and you can see that we sort of have this pyroxene mineral signature that was lying from the stuff that's underneath the ejecta, and then you have this red ejecta that's on top of that. The red ejecta is the altered material. So the thinking is, these are all figures from Sheridan-Akis, that the crater, Huygens crater, sort of disrupted this altered unit here that was in the subsurface and broke things apart, and there are pieces of it sort of sitting in the subsurface, and we were able, with this sort of unnamed crater, to impact into this and eject it onto the surface. So we definitely have a subsurface story here in this crater, which is really fascinating and doesn't really leap off the page when you first look at it. So that's why I think, taking a closer look at a lot of places on Mars, we might find really interesting subsurface things going on. All right, so here we are showing this unnamed crater, and we're going to take a look at this little spot right here. And so here's CRISM imagery of this crater, and we see detections of carbonates. We also have kaolinites, smectites, and chlorite sort of all throughout this region. The landing zone would be right here, so we'd land on it. The carbonates obviously are interesting to explore. These are related to the carbonates I mentioned at the beginning, where this carbonate potentially related to this big, larger alteration event that occurred on a regional scale. The phyllosilicates and smectites also sort of a part of this story. I also have chlorite in this area, which is a little different, which might suggest a little higher temperatures, potentially. Another area sort of around the crater rim, we see a lot of valley network formation. So this is a great site if we're interested in valley network formation. How do they form? What the history is? The coverage, we have some coverage. We don't really have spectral signatures that go along with these things, and that's pretty typical. But how do these things form, and what was the water source, and what was the timing relative to other things on the planet? Okay, so the lava flows are really fascinating on the inside of the crater. You take a look at some of this thermal imagery, and it gets really interesting because there are these blocks and islands, and it looks like things have been all twisted up and turned around. I think right here we're looking at two different lava flows, the darker one, and then that shows it darker in the thermal imagery, and then a lighter one that flowed over the top of it. Anyway, we're going to have a great opportunity at this landing site to do work on volcanism, volcanic compositions, petrology, as well as chronology. And that's a CTX image of the same area. So you have the wrinkle ridges and all of the great things that go along with volcanism on Mars. The other thing about the crater is they got a strong olivine content. So you get, so you also have olivine and calcium pyroxene. So a lot of olivine, a lot of chance to investigate high olivine content materials on the planet. Also interesting textures. So resource-wise, we'll go back to this crater. We're going to land on the resources themselves. The crater has a lot of different interesting hydrated materials. Maybe Montmorillonite's our best hope for resources, for water resources, but also a fair amount of kaolinite. So we also have the benefits of kaolinite that Jack mentioned yesterday. Milkshakes. I'm not a spectroscopist, so they wanted to make sure that they showed that these detections are actually real. All right, so I'm going to be hopefully fast here. Rubrics. So basically, I think that we have. I think maybe it's important to talk about what we're not seeing. We're definitely not saying that this is potentially a place for present habitability. The subsurface carbonate deposit, I think, is something that probably is from the past. So it's our best. I mean, it's a good chance to go look for evidence for past habitability. Hopefully the presence of carbon suggests that there's potential presence for organic matter in the surface exposure. We also, atmospherically, we have a lot of high elevation, and so we have, and low elevation changes, so a lot of diversity there. I think that there's a high probability of surface atmosphere exchange and active trace gases. I think the fact that you have these subsurface carbonates, in other places we've seen serpentine associated with it, I think that we have very strong potential for this to be a methane source or other trace gas source that might be in the subsurface and coming to the surface. So this might be a place where you see trace gases coming to the surface. We have datable surfaces with the extensive lava flows and evidence for aqueous processes in the valley networks. And let's see, there was one more thing I wanted to talk about. Yeah, I think this Noachian or pre-Noachian bedrock. I think a lot of sites will get to see this, but being able to go to the Southern Highlands and look at the sort of Noachian geology, including the Hellas formation, Hellas impact ejecta, and sort of events related to that, I think will give us a lot. I mean, that's a big part of the planet, so it will give us a lot of information about the history that went on there. Resources, we're basically focusing on these hydrated minerals that are in the subsurface and being exposed through impacts. This is impact ejecta, so this is stuff that we hope will be easily mineable and something that can be scooped up more easily than something that's bedrock. And the potential for ores and stuff, definitely not sure. I mean, it looks like we have we definitely have water-rock interaction, we have formation of carbonates, we have subsurface hydrothermal potentially environments, so you might have formation of ore type kind of mineralogy, but that remains to be seen. So data, obviously more high-rise CRISM to sort of sort out this stuff. The area itself is not very well covered. High-rise stereo obviously is something I think a lot of people are talking about and is important for better landing site characterization. I also think this subsurface geology story is interesting, and it may not be as easy to find, and I think it sort of might peak out in different places. So the bit more careful and the more coverage that we have of the right kind of places where you might get a peek into the subsurface geology, I think will help us learn a lot about what's going on. So there's a major subsurface story here, I think, and additional data that leads in that direction obviously would be wonderful. We know we have lava flows in the crater. We know that so it sort of always brings up the question of whether or not there were hydrothermal systems set up as well. And potentially this carbonate is one from this post-impact hydrothermal system. All right, so thank you very much. Thanks. That was the last one, right?
No, you weren't up. Oh. Go ahead. We have one more. It was a good talk.
I thought we were going to discussion.
Okay, so we have one more presentation this morning, then we'll get into discussion period. Pascal Lee and company are going to talk about a site at the western end of Valles Marineris. Pascal.
Good morning. Thank you for staying. It's the last talk of this session. But before I move along with our talk, I just wanted to thank the organizers. This is a dream come true. it's beyond historic. Human mission to Mars has been dangling ahead of my future in my little life, 20 years ahead of me for the past 40 years, and I'm over 40. So it's still 20 years ahead of us, but somehow this is a big step forward, and I really wanted to thank the organizers and NASA for this kind of forward thinking. It's a good time to plan for going to Mars, and indeed the selection of a good site is going to be really essential. This is a relatively large team effort, but it's still just beginning. So a lot of the results are not things that you might want to hang your coat on yet, but it's a really exciting site. It didn't even have a name. It's sort of between Valles Marineris, that you see at the bottom of the image here, and Noctis Labyrinthus, which is this labyrinth network of fractured and blocky mesa type of terrain. And the zone that's in between is essentially a depression. It did not have a name, and so we hopefully made a wise decision calling it Noctis Landing. Noctis, incidentally. Okay, yeah, sorry. On the map, and I'll show you the map later again. It's here. So Valles Marineris, Noctis, and then the Tharsis region here, right at the boundary, and Noctis Labyrinthus is right here. Right. So just to give you a little bit of background, the whole science team that's behind this has quite a bit of experience with field work. Chris McKay, John Scott are names you will probably recognize quickly. Brian Glass in the Arctic and Antarctica. I myself spent a year in Antarctica when I wintered over there. And also I did 5 additional summer campaigns looking for meteorites and drilling for ice cores. But this is where my first experience with driving essentially rovers across unprepared terrain over long distances began. And so this is a view up there of Dumont d'Urville Station on the upper left. It's at the coast, but we drove inland onto the continent to go to an ice coring site on a vehicular traverse. The base that we had on the coast is shown here on the upper right. So we were bringing in some experience with operating out of a base as well. And of course, in the lower right, you have a typical scene of an ANSMET meteorite collection campaign. This is an aerial photo actually taken from a kite. There you go. So the other source of experience came from 19 consecutive summer field seasons on Devon Island. This coming summer will be our 20th consecutive summer on Devon. And Devon Island is the largest uninhabited island on Earth. We go there because there's, among other things, Houghton Crater, which is a large, well-preserved, 20-kilometer wide, 23-million-year-old crater. It's an impact crater. But the thing that really draws us to this site is, in addition to the crater, a lot of the surrounding geology and the fact that the entire setting is that of a polar desert. So if you go to Alaska, you're still dealing with tundra. Most of Siberia is tundra. It's relatively wet. This is a corner of the Arctic that's both cold and dry, which makes it very attractive, and it's also free of ice in most places, unlike the dry valleys of Antarctica. We also have a base there, and the experience that we bring in this case is the fact that we actually set up the base. We had to go through the process of selecting a site. This is not the first location where we camped, but we settled on this from remote sensing surveys and ground surveys, and now this camp is a permanent facility that NASA has been using every summer since it was set up in 1997. Over the years, this is essentially Devon Island, but with the same circle code and ROI sort of coding that has been used for most of these talks. Over the years, most of our activities have been within 20 kilometers of our base camp. But that's not necessarily a reflection of our desire to go farther. It was mostly limited by the resources we had, the fact that we did not have things equivalent to a pressurized vehicle for a long time. But you also see some longer traverses that are the white dotted lines that have taken us up to 200 kilometers or so away from our camp, or driving from Resolute Bay on the lower right, on the lower left to our camp as well. So my point here is that there have been some long-range 200-kilometer class traverses in connection with our base camp over the past years. Now, just to add some more perspective on this, on Apollo, there was a sort of a three-step process for you to get to an outcrop. You picked a target region of interest. There were lots of discussion before we selected landing sites. Then once you get there, you have an unpressurized rover to take you some distance away from your landing site, but not that far in the end, because you have to be able to walk back. And then once you got to something that you might call an outcrop or a boulder that you wanted to sample, you would step off of your rover and do the final hike on foot. So you sort of want to limit, especially on Mars, given the higher gravity, how much walking actually you want to do and have a good mobility system to support your traverses. At Houghton, we've been pushing this one step further with Mars in mind, and so our base camp becomes our target region base. This is sort of exactly what we're trying to select here for Mars, but the notion is that we would use a pressurized rover to access regions of interest, and we'll talk about how far they can be considered, but they should be, I think, more than 100 kilometers away in radius, at least down the road. Accompanying our pressurized rover simulator, we use Humvees here. We also have ATVs that, in the context of a Mars mission, might be robotic ATVs that would follow the pressurized rover, and then you can use them as a personal unpressurized vehicle once you get to a site of interest. And so that's shown in the lower left. You get to your site of interest. You now do the local exploring by ATV. Your pressurized rover is kept in a safe place where it remains in comms contact, for example, with the rest of the world. And then once you get to your outcrop or your boulder or whatever you want to sample, you step off of your ATV and you go sampling. All right. Now, we also have longer range experience with rover driving. Recently, we did the Northwest Passage Drive expedition. Shown here on the right is sort of the map of the first traverse of that expedition, which was about 500 kilometers in length. It took us 8 days. And this was on unprepared terrain, all of it on sea ice. And the sea ice was not smooth. It was pretty hummocky. So the notion that we could, down the road, once we get comfortable and familiar with Mars and have shaken down the systems, the notion that we could do traverses that are 500 kilometers in length should not be shocking. They could be done in a week each way. So in 2 weeks you could go pretty far. Yep, there's more that you can find out about this experience. We have a paper that was mentioned earlier this week in astrobiology, and there's a movie coming out, a documentary on our traverse called Passage to Mars. So Noctis Landing is at the junction between Valles Marineris and Tharsis. There are a few assumptions in our choice of this site. First of all, we believe that we really should be picking a fixed base, not consider a mobile base. That the first landing site will be our long-term base site. The scouting should be done by robots and therefore not astronauts. We'll focus, of course, on astrobiology, sort of an all-encompassing term. And the reason why this site is of interest is because Valles Marineris is the mother of all road cuts on Mars. Tharsis is the mother of all volcanic provinces in the solar system. And it also is a place where if you want to eventually access the deep subsurface of Mars, you might benefit from a higher geothermal gradient and also less crust to drill through. So it's an exciting site from that perspective. So here it is. And you can see that it really is sort of a prong into the Tharsis region, and meanwhile it remains at an altitude where you can land. It's also in a higher range of altitudes among the sites that are permissible. Okay. One thing I want to point out is this crater in the foreground called Oudemans. Oudemans is the largest crater of its class, 125 kilometers within 1,000 kilometers range. That's well preserved. And Oudemans is believed to have excavated essentially the stratigraphic column and even deeper than is exposed in the deepest parts of Valles Marineris. So I'll point out later why Oudemans is so exciting compared to possibly a site that's in the middle of Valles Marineris, mainly because Valles Marineris is the different layers are not necessarily easily accessible, even when they are just a few hundred meters away. So this is our landing site. The color coding is topography. You can see that the landing site itself is at minus 300 meters or so. Meanwhile, to the south on Syria Planum, we're dealing with a plateau top that's at 6,000 meters. So there's a considerable change in altitude here and lots to see stratigraphically. The site itself presents a variety of textures and topography, smooth depression, presumably sedimentary deposits, and remnants also of Valles Marineris type canyonlands. The targets of interest, I'm going to go, they've been categorized. So within each category, say science region of interest 1, there's site A, B, C, and D, etc. This is the landing site. So it's, I just wanted to point out that it's benign. And we're told that, okay, this is within a few kilometers from the landing site, so there is some sand. And incidentally, I don't think we should think of avoiding sand. I think we should just conquer sand on Mars. You will run into sand at some point very quickly in all your excursions, so you might as well consider that sand as something you just have to deal with and not have to worry about with a good mobility system. Some of these deposits are, which presumably are made of hydrated minerals, just like they've been identified in many locations, east, west, north, and south of this spot, are sulfate rich. Some are buried, presumably in volcanic, in sand that's dominated by volcanic materials from the nearby Tharsis region. This is interesting because sulfates in the Arctic actually are in a preferred habitat for cyanobacteria. They find nice shelter within the layering of the selenite sulfate that we have up there, and so it's both shielding material for UV and meanwhile allows light in, and so there's actually some interesting biological potential for sulfates. Outcrops with different levels of exposure. Some are barely exposed, like here. Others are massively exposed in layered sequences that you can see in the middle of a pit. So this pit is about 12 kilometers south of camp, of our landing site. Others are possibly about to expose some of these gypsum beds, or I should say sulfate beds, so we're not of course sure. And then of course further into the Eos and Titanium Chasma regions, there are massive exposures of some of these presumably hydrated mineral deposits. Okay. All right. There's also a long history that's recorded, of course, being in near Valles Marineris. The very bottom there, we might even be dealing with Noachian outcrops with an Amazonian cap at the top and Hesperian stuff in the middle. No RSLs that we can identify immediately, but they wouldn't be surprising. Most importantly, in this whole region, a lot of downfaulted, tilted chunks of Valles Marineris, so that you can actually explore the entire sedimentary column, or a good chunk of it, without having to climb. You find a good location where they are tilted to about 90 degrees, and you can just walk along the outcrops and sample. There are direct drainage channels, and which might be indicative of water episodes, liquid water episodes. And then most importantly, farther south, Udemans, a magnificent crater where near the central peak you have gigantic mega blocks that are downfaulted. There's also ejecta material that you can find within a 100-kilometer circle from camp, from base, including, so this is believed to be an ejecta mega block from Udemans that's sort of mangled and exposing layered rocks that are similar to the ones you would find in Valles Marineris. Again, the same idea. You have mega blocks that are already broken up and tilted for you, so that you can just walk horizontally and explore the vertical sequence of Valles Marineris. These are just more examples of that. Finally, there's Noctis Labyrinthus itself, which is an amazing place with mineral deposits at its bottom as well, hydrated mineral deposits at its bottom. McEwen and others have documented this very nicely. And along the walls of some of these blocks in Noctis Labyrinthus, you have these massive layers as well of presumably hydrated deposits or carbonates or sulfates. All right, resources, only two kinds. These hydrated deposits, galore, and of course the sand. As much as I like the idea of going into a cave down the road, I think we might find natural shelters. I think for early missions we should be looking at just sandbagging, which is a very mature technology. So you can look at this in more detail. We don't address everything. The site is not perfect. We do need more data, of course, but one thing I wanted to sort of encourage is the thinking that we might fly drones around to really scout out the site in detail and more comprehensively than it could be possible by a rover. So in conclusion, just these 6 takeaway points. It's a strategic site from a scientific and operational point of view. It's at the crossroads of essentially everything that you would want to find out from Mars, and especially you could access other places from it. Oudemans could offer a horizontal way of accessing the stratigraphic record that's exposed in Valles Marineris vertically. We should plan for 1,000-kilometer radius exploration zones. I think we should be not too shy about that. The excursion time is more important than the distance traversed. The issue is sort of how long does it take you to get somewhere as opposed to how far it is. You could be at the base of the wall of Valles Marineris and it could take you weeks to get to the top if you had to drive around. More data, of course, is needed, and drones are recommended. Finally, analogs are very important, and I hope we do more work. Thank you.
So
Okay. Oh, go ahead.
could I have the speakers from the other sessions come on down here in front, and we'll have a discussion period.
Okay, we got the mics ready. Okay. So big thanks to everybody for all the presentations too. This is really cool stuff. See, you guys got a mic, and I'll just use this one, and we got the other mics ready. Okay, let's open up to questions. Right here. You right? Yeah. Come up.
I had a question for Joseph. You mentioned that the oldest extant crust on Earth is 3.8 billion years. But do you think the detrital zircons, for example, might have any relevance to looking at early biosignatures on Earth? And if so, is there any analog or relevance to that with Mars?
Maybe and no.
And can I get
I mean,
you
I
guys
think they're
a little
relevant
closer
to-
this way? Sorry.
They're relevant. Zircons would probably be relevant to understanding the onset of tectonics and formation of continents and subcontinents, and that is related to sort of origin of life studies in a loose way. Relevance to Mars, I think, is probably, not to be funny, but probably no.
So there's no direct biological relevance in zircons, you don't think?
In my opinion, no.
Can I ask a quick question of? On. Hello.
Hang on, Joey. Can we figure out?
Hello. It was just on. Oh, okay. There it
Okay.
goes. So, Joe, I wanted to pick at your deep life thing for a minute. You said, so why are we looking at surface life? And you postulated that it was because, we're looking for photosynthetic life. And I'd argue, I don't think we've ever really talked in detail about looking for photosynthetic life on Mars. I think we've always talked about looking for chemoautolithotrophic life at the surface. And the reason you might go to the surface to look for that is because the redox reactions that drive that kind of life are often driven by surface-atmosphere interactions. And it's that kind of, high, very high redox gradient you can get from that kind of interaction that would be very beneficial for that kind of life. So I think that's the main argument for going to surface environments on Mars.
Okay, I just think that our bias, having come from this planet, is that so many ecosystems are ultimately driven by photosynthetic energy sources that get sort of cycled through the food chain, so to speak. And if what you said is, if that's true, then you need to find a niche which benefits from all those redox gradients but doesn't suffer from all the disadvantages of being at that sort of critical zone area. And it's just, basically my point is that it's a discussion we need to have about trying to discover our own biases.
Agreed.
Really.
Yeah, I just wanted to second this idea. Chemolithoautotrophs can live on the surface. They can live in the subsurface. As far as where water is stable, most stable, where environment is most stable, it seems like the subsurface is the best bet for that. Now, there's a lot of talk about preservation, and I know we're going to talk about that in a second, but I think that you got to go where they're living first before you can hope for preservation. So.
Okay. And I'd like to ask.
Well, I have a comment
sorry.
about
Go
that.
ahead,
so-
please.
Well, I mean, yeah, you have to go where they're living, but I think
Come on,
that,
come on
you
over.
know,
Here. Come on.
And I'm so sorry, I missed part of Joe's talk, but I mean, from the experience in the subsurface environments that I'm experiencing, it's not hard to find where they're living, and we can also get preserved. So the environment that I study is a near subsurface environment with that groundwater flow. They're living in that environment. They are assembling according to the mineralogical assemblages in that environment. Specifically, they're assembling according to the sediments. And that is a preservable environment. If my analog basin dries out, those microbes are going to get preserved. So I don't think it's hard to, I don't think it's either or. I think we can find that environment where they're living and they can be preserved.
Right. And hang on one second. Okay. So when you ask a question or have a comment, can you introduce yourself? Part of this is about building community, so we need to start doing that a little better. So new rule. Okay.
And Joe, just with regard, again, I'm sorry I missed your some parts of your talk. With regards to kind of that near the near surface microbes, you don't, you can have that chemolithotrophy without relying on without relying on photosynthetic organisms. You can have a community that does not rely on having a photosynthetic basis feeding into that community, if that makes sense.
I was actually, I wanted to sort of speak to that. Lindsay Hayes, JPL. Mars
Thank you,
Planet
Lindsay.
Office. You haven't seen me before. I just wanted to add, though, that, I mean, we have to remember that there's a very strong Earth bias in all of
That's
this.
true.
And that chemolithoautotrophy on this planet, if we're talking about redox gradients, the surface is so oxygenated because we
That's
have
true.
billions of years of photosynthetic activity. So, we have to sort of balance that if we're thinking about a very different potential ecosystem on Mars, because we're not necessarily going to have that same push coming, the balance between, a more reduced mantle and a more oxygenated surface.
Yeah, no,
so I just wanted to comment.
no,
on that.
you're absolutely right, and that's a very good point,
Okay.
very true.
Great, thank you. I think we got a question back. Introduce yourself, please.
Jake Bleacher, Goddard Space Flight Center. I wanted to have a slightly different discussion about life, namely the humans who will be landing there and trying to help keep them alive. And I've heard in a number of the talks a little bit of mention about protecting the astronauts, and Pascal talked a little bit about sandbagging as a means of protection. We've heard about going into caves, making our own caves. So Joe touched on magnetics really briefly in going through his chart there, and I wanted to go back to what Paul presented on the first day as some of the cross-cutting themes. A lot of what we're talking about so far has been very astrobio and geoscience focused, and which is fine with me. I'm a geologist, but going back to some of the cross-cutting themes, magnetics has an important aspect to this, not just a pure research itself, but when we were going through the MEPAG study, the magnetics community expressed some interest in being on the ground and doing some high-resolution studies of the magnetic fields as potential for protecting astronauts and maybe some of the life that the astrobiology community is talking about from harmful radiation. So I just wanted to make sure that one little bullet that Paul went through really quickly is actually represented and thought about a little more. I think Laura Kerber is one of the few people I've seen so far talk about the magnetic signature near the landing site she's talking about. So it's not that the magnetic fields might make a safe zone, but they might make a slightly safer zone for long duration stays, and that might make a big difference when you're there for a long time.
Okay, and right here, introduce yourself.
Artemis Westerberg, Explore Mars. I actually was interested in the same thing because when I set out to pick our spot on Mars, was driven by the idea that the magnetic remnants would perhaps protect the humans we are sending, and I would like them to give the best chance to do their work there and get back home and safe. However, I was driven by my colleagues, as I'm not a geologist, to ask Chris McKay and some others about this, and Chris pointed me to a discussion that apparently had been raging or had been done in the last few months. And he pointed me that Rebecca Jolitz did calculations, and as far as I understand what it says here, it means there is some protection, but it isn't more than 20%. So it's not. So it's a redux. I mean, 20% is still 20% less radiation, but it's not the same. Oh, you know.
So let's let the panelists. So you go ahead and address both questions if you could, or comments if you would.
This is generically it's a good idea, but the thing is, what's detected on Mars is a remnant magnetic field. It's not an actively generated magnetic field from a dynamo. The magnetic field levels, the intensities we're talking about on Mars are less than about 100 nanoteslas. The Earth's magnetic field is about 70,000 or so nanoteslas. Just to give you a sense of how little protection you would be afforded anyway by remnant magnetization. So that's actually the main issue. Having said that, there is research that's being done about generating intense magnetic fields locally. And I know, I'm aware of the efforts by Jeff Hoffman at MIT about this, but there are other efforts that I can't name that are going on about creating shielding, radiation shielding from intense magnetic fields. But you need something intense. You can't just use the remnant magnetization.
And Jim, hang on, Jim, we're coming to you, but let me finish to let the panelists. You guys have any comments you want to make? Hey, hang on, get us mic.
It's probably going to be something related to what Jim might say, but I think the reason I sort of blew through that comment and I said, well, good luck, because the coarse, if I understood the question correctly, it's related to the remnant magnetism we see in the crust, which is at such a coarse spatial resolution and limited so much, because I think Ross Irwin contends it's just been buried by thick amounts of resurfacing from Argyre and Hellas and all that stuff. Maybe you don't agree. Be curious to hear what you think about that. But I think the real point is for upcoming missions is if that's information that we think we need to have higher spatial resolution and more sensitive remnant magnetic mapping, that's a really good point, is that if that's what we need, then we need to get more data.
And figure out how we capture that idea for tomorrow, too, please. And then Jim,
Okay, so just a quick comment. Jim Head, Brown University. So the history of the magnetic field is really critical in understanding just about every aspect of Mars. And one of the things I'll talk about is, in fact, I think we have a place where we can actually sample the geological units of lava flows, the sequence of lava flows, to actually test the idea. Okay, when did it stop? How did it evolve? So the other thing is, if we're going to explore the details, we had a mission, discovery / scout mission airplane, okay, Ares, which in fact flew over the surface of these magnetic anomalies, and we could look at the polarity and the detailed structure. So there are ways to do that, and it's a really critical thing in terms of the history and understanding of how the magnetic field operated in the past. So those are two things that bring us huge amounts of knowledge about biological activity, potential, et cetera, et cetera. So that's just something we shouldn't leave out for sure.
Okay, next question. Yeah, Alex. Introduce yourself.
Alex Longo with the Cardinal Gibbons High School. I was wondering a bit about Huygens Crater, and because it's an older crater located in the Southern Highlands, could we potentially sample ejecta from hundreds, if not thousands, of kilometers radius all over the planet in that your EZ?
Yeah, something I didn't really emphasize is that Huygens it's a big crater. You have a lot of opportunity for cross-cutting relationships. It impacted lots of other things. It's been around for a long time. Lots of other things have fallen into it. So, yeah, absolutely, it's an excellent place to explore those kinds of relative age dating as well as the absolute age dating.
Okay, great. Next question. Or Joe, want to have any other comments about that? Okay. Okay, next question. Jim, you got one? We're good.
So just talking about the white layers in the upper part of the crater in the interior you were talking about. So Jim Head, Brown University, sorry. Are those like deposits, or are they part of the stratigraphy? They're deposits, right? Can you just clarify the stratigraphic relationships between the crater formation and the filling, et cetera?
As far as we can tell, they are deposits that were deposited when the actual the crater infilled. They were somehow deposited in the ring. Now, how exactly they were deposited, we're not sure, but best guess right now is they are deposits. Is that right? Yeah.
Okay, and if you have a Rob Mueller, and if you're in the back, the lights are really pretty blinding, so move your hand a little bit and I'll try to get to you. Rob, go ahead.
Okay, Rob Mueller, Kennedy Space Center. I want to poke a little bit on what Pascal said about aerial surveys and access. I've been in Houghton Crater with Pascal on an expedition, and one of the things that struck me was the scale of everything. Sitting here in this conference room, looking at these maps, doesn't convey the scale of it. And when you're standing in one of these valleys looking up or looking down into a canyon, it's really an experience as a human. And I don't think we're adequately conveying that here at all. I remember Steve Hoffman was giving us instructions on where to drive, and I don't know if you did this intentionally or not, Steve, but it was go from point A to point B, but there was a big canyon in the way. And so Steve said, well, it's not my fault, the pixels didn't show that. I'm just giving you what the orbital data says, just go to B. But the result was a 3-day detour. It had an impact on us. We were running out of food. Luckily, we all got along.
And conversation.
Well, the conversation didn't matter so much, but it was because we were busy, But the thing is, what I'm trying to say is there's a human experience here, which we're not conveying at all in all these slides, and most of it's to do with scale and access is not adequately conveyed here at all. And I think the only way to do it is from the air, and you need some kind of aerial scouting, and then you can make better decisions on the ground.
Any comments?
That's a good point, Robin. The one thing I should have said is I don't expect us to somehow launch ourselves on a 100-kilometer traverse from the get-go. You would establish routes. That's what we actually do typically at camps and even in Antarctica. You establish routes over distances that you become familiar with. You cache things out, supplies of fuel and food, and then over time you create a logistical chain that allows you to safely access 1,000 kilometers. That's very conceivable. So it's a progressive thing. It's not one of those things where you just go out there.
Okay, hang on. I got a question right here, and then we'll come back to you.
Yeah, Fred Kale of JPL. I just want to comment on that idea of access. Using example of Gale Crater or Meridiani. We've driven a marathon with the rover on the surface. We can do that planning from orbital data. We have very good ideas about roughness and slope and access to cliff surfaces. We have over a decade of experience of driving on Mars. We can figure that out well before we get there, which cliff faces are accessible by whatever vehicle that we're using. These things can be done well before we get there and landing.
And then back here.
Yeah, Jake Bleacher, Goddard Space Flight Center.
Oh, sorry, Jake. Hang on. Oh, okay. Did y'all have any comments at all? Okay, Jake, go.
Yeah, I was basically going to say the same thing, that the airborne aspect, which Stan Love brought up the other day, is a very important intermediate level of data between orbital and on the ground. But also, one of the things we should be talking about is what do we need? We're talking a lot about orbital data to help us characterize these sites, but we really need to continue to think about, do we need precursor missions? Because when you do put humans on the ground, a lot of times you're going to be expecting access to certain locations through certain pathways, and you end up with what I, from field experience, like to call potential choke points. You go over the same place over and over and over. We need to understand if those little bridges are going to degrade through time. It's not a matter of one small rover going over at one time on its way to another place. It's a matter of people tramping through there repeatedly. Recon on the ground, complemented by the airborne data, is really, really important to maintain the safety of crews who are going to be there for 4 or 5 missions we're talking about at this point at the same location. And I'm sure Pascal has plenty of thoughts about that from his field work as well. But it's an important point, complementing all these things together.
All these are good points. And the thing I would add, though, is planning a traverse on a relatively flattish terrain, even with hills, but where
where you actually can have enough data from remote sensing is perfectly fine. As soon as you hit canyon lands, steep vertical cliffs, you don't even know what outcrops you might run into. And this is where aerial surveys at that scale are sort of side-looking aerial surveys become valuable.
Yeah, okay, right here, and then, let's see, Jim, I'll come get you. And then we're maybe out of time, but we'll try to get a few more in. Go ahead.
So this is one thing that, oh, thank you. Robin Ferguson, USGS. We're talking a lot about the additional data sets we might need, and also at different scales than what we currently have, which I think is an important discussion to have. But as we talk about new data, more data, we also need to talk about the infrastructure we need to integrate these data sets together in a meaningful, controlled way so that we can go from one data set to another very, very accurately. This isn't a simple process or a cheap process, and it's something that needs to be folded into our discussion when we're talking about humans depending on our accurate integration of data. So I just wanted to throw that out there, maybe to talk about more tomorrow.
Yeah, that's fair. And so I actually would like to ask you to go further than actually on Jake's thing, because I'm seeing a lot of nodding heads here despite the blinding lights. And the point being is that if you actually can start framing up a statement that tonight, I'm going to throw the ball in your court, that will help it, because that'll help everyone here. We get all of their brain power on it. We can really hone something that will help achieve a lot of these things. It's as you say, it's the beginning, but it's a start.
So where would you like us to submit such statements?
You can send it to me, or that's fine.
Okay.
Yeah. Okay. Jim.
Yeah, Jim Hedbrand, University. So I think it's really important for us to think about the complementarity of human and robotic exploration. We're talking a lot about now precursors, which we do to get to there, but once we're there, there's all kinds of things that we can really do. So I worked on Apollo, and we looked into things like lunar flying units, extended mobility units, all sorts of things to complement and extend. I worked on Apollo 20, 21, and 22, which none of you have ever heard about. But it was going the plan was to take a rover, which had an extended vehicle on the back, and once the astronauts left their sortie and went back to the Earth, they would in fact set that up to be robotic to go to the next landing site and do traverses and analyses for 500 kilometers between the landing sites. So it was very much an interpolation and extrapolation. So these are the kind of things we need to think about in these areas too. We need complementarity, we need extension, interpolation, extrapolation, and so human-robotic interactions. Get the human to be able to do what they do best, which is the observations and geology and scientific analyses, and then use the robotic to extend and also to complement. So it's something I think we really need to think about in terms of our long-term plan.
And one correction, send it to Steve Hoffman, because I'll take it too, but it's much better to go straight to the guy who's going to lead it for us. And then we're going to stop here because we're on the break, but I did want to let the panelists, actually, if you all have any additional comments, I'll give you all the last word, because I've talked too much.
Did I mention that where we are, we're very close, within 1,000 kilometers, mind you, from the most recent lava flows that have been identified on Mars that are presumed to be less than 100 million years old. 1,000 kilometers, that's a 2-week drive if all goes well.
Okay, any other comments, guys?
So lastly, I really do believe strongly that the idea of solving the mystery of life on Earth will require leaving the planet. So if we, those of you who agree, if we can communicate that effectively to people, I think that will help our cause. And now, these specific questions of whether photosynthesis is something to consider on Mars, we have to sort of educate ourselves. People like sort of with my geological sort of background, I don't really have that much biological knowledge, and I shouldn't be arguing for or against certain things that have major consequences. But that's the kind of discussion that would help all of us to have, I think.
I saw a biologist nodding when
Well, I just wanted to say I definitely agree that we need to have those conversations, and we need to kind of consider our biases and what we know about life on Earth, and we definitely need to consider, how different, not just photosynthesis, different metabolisms factor into what we can expect to find on Mars. The other thing that I wanted to point out, and I feel like a lot of authors have been doing a really good job, hopefully I did a fair job on my side, is we really need to think when we're talking about habitable zones, not only where these microbes can live, because we do need to go where we think that they can actually live, possibly originate and thrive well, but we need to consider where do they preserve well so that we can actually find evidence of them. And that's one thing I just want all the site presenters to kind of take away with as they're going through their analysis is where you have your habitable zones where you think things could live, really, really think about that preservation. What is the preservation mechanism at play? Can you really preserve biomarkers, and what kind of biomarkers or biosignatures do you think can be preserved at your site? I think that's really critical for the astrobiological portion of this exercise.
And pause on this.
Yeah, I just want to come back to the remnant magnetism side. It's a conversation I think that was really great, and I think we know a lot of remnant magnetism here, and there's not a lot of landing sites. So, I think that's something we should keep considering.
Okay, so we're going to break for 15 minutes, so we'll see if I do one. We'll pick up at 10 till.